introduction. I'll just share my screen. So hopefully that can be seen. Phil, please jump on if that isn't visible. So yes, I'm a product of the Marshall's Aerospace apprenticeship many years ago now, but it certainly stood me in good stead for the challenges that I face now. And I'm not going to be able to cover all of them, but I'm certainly going to touch on what I consider to be the bigger technical challenges that we face here at Vertical Aerospace. And it's going to centre a lot around the electrical propulsion system, which I guess makes a lot of sense, as that's part of the new area of development for eVTOLs. But before I do that, I will also cover a bit about Vertical Aerospace, our history. It's not so long, but I think we've covered quite a bit of ground in our short existence. We've had a guiding phrase. I think the wording might be slightly changing now as we're growing, but the philosophy is the same. Really, it's about developing technology to enable a lot more accessibility to personalized flights. So the whole concept of hailing a cab, a flying cab, really it's trying to make that a reality. The focuses we have here are to make it accessible, on demand, and carbon free. The company was formed by a guy called Stephen Fitzpatrick. He's the founder of OVO Energy. I think they're now the second largest supplier of electricity in the UK. And he founded that 10 years ago. And about 5 years ago, he wanted to start looking into how to electrify aerospace. And how to overcome some of the challenges faced by helicopter flight, because there is already a VTOL option, and why not just electrify a helicopter? There are some really good reasons why not to, and I'll touch on some of them later. But one of the things Stephen was really focused on is not just becoming another aerospace company. Obviously needing some aviation capability, so systems architecture. There's been a lot of electric flight development in the mainstream aerospace companies, and also the regulation side. But combining that with his current area of expertise with OVO around renewables, battery technology, the ground infrastructure area of our development is very well covered by his ability to provide electricity, but also coupling that with the fast-paced agility of Formula One and also automotive. So battery technology is really advanced in automotive, as well as motor design, inverter design, lightweight structures, crash capable structures is very much developed in the Formula One arena. So Stephen brought these different industries together and created Vertical Aerospace. Now, Vertical Aerospace started out really as six guys in a shed. It's almost a stereotypical kind of start point for this type of company, where it was 6 people playing around with whatever technology was available at the time, and the output of that was the we call it the proof of concept, the POC. We now call it VAX1, and that really was demonstrating that the technology, today's technology, or 2017's technology, was good enough, and just good enough, but good enough for electric vertical takeoff and landing. And they created a vehicle. It was actually fairly capable. It could carry the payload of 1 person, although it wasn't sufficiently developed to actually put a pilot on it. Based on that, the company grew to in 2018, about 30 people, we started working on what we called Serif. We now call it VAX2. So X1, one person, X2, two people, and you'll probably notice a theme running there. And we flew Serif. I will touch a bit on some of the technology and the development of Serif in a bit. But we also acquired a company called MGI that is or I guess it still is a Formula One consultancy company, very much specialized in carbon composites development for the Formula One industry. And we acquired them and created Vertical Advanced Engineering. We grew again in 2019, finishing 2019 with about 70 engineers and a company size of about 110, something like this. So touching on the proof of concept, the POC, and now named VAX1. The challenge here was integrating already known systems together into a flyable 750 kilo full-sized vehicle, and flying this around Kemble Airfield. It was under the full coverage of the CAA, so it passed a number of checks to ensure it was safe to fly. But that it wasn't good enough to turn into a product. It didn't have sufficient safety levels in any of the systems, so any failure actually would have led to a loss of the vehicle. Thankfully, that didn't happen, but that's certainly not safe enough for aerospace. So from that, we moved to Serif, now VAX2. And one of the clear differences you'll see is the number of rotors. So we've gone from a quadcopter 4-rotor vehicle to 6 arms with 12 rotors. Now that's really focusing us on how do we create redundant systems? How do we make this vehicle tolerant to a failure of one of the propulsors? Now, we did a lot of modeling around this, and we also successfully flight tested a failure of one of the propulsors. It was designed to fail 2 motors, but we decided not to push our luck on this vehicle, and we settled with just failing 1 motor and continuing safe flight and landing. But really, the challenges here were not just about developing that redundancy, but it's developing our capabilities. So we're growing as a company as well as developing our product. So we need to develop all of our tools, our techniques. Now the image you see, and I'll touch on it a bit in a second, it really shows the interaction of some of these systems. So there's the rotor, the motor, and then down the side of the arms that are supporting them is the cooling system. So the rotor is providing the cooling for the motor and the inverter. So there's a real close coupling of these systems, and that capability we needed to develop. We have to develop everything in-house, so we needed to develop that capability, and that's quite specific to this application. So we end up having to design our own rotors to meet this specific need. And here you can see the insides of that housing. It's nothing particularly special, but it's really showing the close coupling of the electrical connections, the cooling system. Obviously, we can't have any leaks. That would be quite problematic. So the care and the criticality of this installation is quite high. Now, what you'll see on the bottom left is a view of the airflow from the rotors. And what you'll see is there's quite a dead patch underneath the rotor at the hub, where you actually don't get very much airflow. So it was really important for these cooling pipes to be running along the length of the arms, because we really take credit of the fast moving airflow. And that's what I mean when we're having to couple the different systems together quite heavily to develop this capability. So just to look at that from a systems engineering perspective, we take an input. So we take the aircraft performance. So this is target operation. In the case of the Seraph, this is 2 people flying a 30-mile mission. We then have a mission profile for that. So a vertical takeoff, a forward flight period, a vertical landing. There would then be a go around, so an emergency aborted landing programmed into this mission. We have some of the flight dynamics, so the accelerations, how maneuverable we need the vehicle to be. So this could be how susceptible it is to gusts, or just is it a direct flight path, or are we having to maneuver around certain land features, mountains, buildings, whatever that could be. There's a number more in this list, but these are the kind of critical ones for the purposes of this. From that, we can then size the motor, size the inverter, and we can track back all the way to sizing the battery and the associated systems with the battery, as well as sizing the lift rotors. So now we know what torque we want the motor to spin at, what's in speed, what voltages we want to run, and out of that we get essentially weights, but not just weights. We also get some features for the control laws that we need to develop. So this could be how fast the motor needs to accelerate, or how fast it needs to decelerate. It could be some control loop speeds, but these elements are then fed out into the wider flight control system.